And here we are on the second and final video for section 3.3, where we have just learned the quotient rule, which, like I said, it makes you sound a little bit strange, but it works. And so we're ready for the second example, example number 8. And we have r equals the square root of theta minus 7 over the square root of theta plus 7. And the first thing we need to do is we need to rewrite this in a user-friendly form. We need to remember that theta, or square root of theta, is theta to the 1/2 power. So it's theta to the 1/2 power minus 7 over theta to the 1/2 power plus 7. And so it's obvious we have a quotient situation, so we need to use the quotient rule. So r prime would be ho d high. Well, the derivative of this is going to be 1/2 of theta, and then half minus 1 is negative 1/2. Minus. So that was ho d high minus high d ho. Well, d ho would be 1/2 times theta raised to the negative 1/2 power. And notice in both cases when I took the derivative, the 7's are constants, so they are 0, all over ho, which is theta raised to the 1/2 plus 7, quantity squared. And once again, we're just going to be able to leave it that way as it stands. Okay, so now let's just clean this up here. So 1/2 theta raised to the negative 1/2 of theta to the 1/2 actually boils down to 1/2. 1/2 theta to the 0 power, or 1/2, plus 7/2 theta to the negative 1/2. That's just distributing this to both pieces there. Likewise, all we have to do is distribute this, and 1/2 times the theta raised to the negative 1/2 times theta to the negative 1/2 would be negative 1/2. And then this would become plus 7/2 theta to the negative 1/2, all over ho. Well, it's very obvious. The 1/2 minus the 1/2 cancel each other out, and the 7/2 plus 7/2 turn into 7 theta to the negative 1/2 power over theta to the 1/2 plus 7 quantity squared. Now we have to write this in much more user-friendly, or not user-friendly, but in more acceptable form. So this is going to become 7 over theta to the 1/2 over, and theta to the 1/2 is the square root of theta. So I can rewrite that like that. But not only can that fit here, but this does simplify, or written in this form. Whoops, not x, theta. Let me erase that so we get something that looks legible. All I've done is I've moved this down here to take care of this compound fraction, and I've changed theta to the 1/2 to become the square root of theta. So it's 7 over the square root of theta times theta plus 7, the quantity squared. Now that's number 8. Now this is the second example of the quotient rule, so I feel we have done enough that now we can use whatever method we really want for number 9. And number 9 looks like this. R equals 1 plus 7 theta over 7 theta times 7 minus theta. and we need to find the derivative. Now here's the problem, or a couple things that I see. First of all, we have a quotient here. So we're going to have to use the quotient rule, but once we use the quotient rule, we're also going to have to use the product rule, and we're actually going to have to use the product rule, or the quotient rule within the product rule. It's not becoming so nice. So I'm going to look at maybe something a little bit different. Maybe I'm going to want to take this 7 minus theta and multiply by this, because after all, this is 7 minus theta over 1, so I should be able to take 7 minus theta and multiply by 1 plus 7 theta and see what that comes up with. And that would still be over 7 theta. Or another way I could look at it is, since this is just one term here, I can give this one term to everything up here, and then this becomes just a binomial, and then I can use the product rule to figure out what that is. Or even perhaps better yet, after finding this to become a binomial and then this a binomial, actually do the FOILing and then just take the derivative of that. So there are many different options that we can do here, and I don't want to at this point actually take the product rule and within the product rule have to use the quotient rule to find the derivative of this, because remember, for the product rule we leave this alone, the derivative of this. Not too bad. But then what we have to do is we have to take the derivative of this, but to take the derivative of this we need to use the quotient rule. Not fun. So I don't want to do that. What I might do, like I said, would take this times this and get a simpler quotient rule, but you know, let's just see what happens if I give this 7 theta to everything up here. So I'm just rewriting now. I'm not doing anything else. This would become 1 over 7 theta plus 1, because 7 theta over 7 theta is 1, times 7 minus theta. But we still don't like this because we have a theta in the denominator. So rewriting this in a more user-friendly form, it becomes theta to the negative 1 over 7 plus 1 times 7 minus theta. Now this one's not too bad, but now this would be a relatively easy product rule, but I'm even going to just go ahead and FOIL this out. So take 7 times that and I get theta to the negative 1. Those are the first terms. The outer terms, this times this becomes negative, what, negative 1/7, because the theta to the first power times theta to the negative first power becomes theta to the 0 power, so yeah, that'd become negative 1/7. 1 times 7 becomes 7, and the last terms would become 1 times negative theta, or minus theta. So this is R. Well, not quite. We need it a little bit more simpler. Putting it in descending form, theta plus theta to the negative 1 plus 48/7. So that's what R is. I think this is much simpler than this. And all we've done is rewritten R in a much user-friendly, more user-friendly version. So now all I have to do is take R prime. R prime, well, the derivative of theta would be 1, because we take the 1 times the 1, and this becomes a 0. 1 times negative 1 is negative 1, and theta is going to become theta to the negative 2 power. This is a constant, so it's going to become 0. So finally, all we have to do is rewrite this into a more acceptable form, and it's 1 minus 1 over theta squared. Realize we could have done the product rule, but when we did the product rule, we would have had to have done the quotient rule. We could have, and we would have ended up with this as our final answer. We could have multiplied this by this and just get a quotient and then do the quotient rule. We still would have ended up with this. We could have done what we did and stopped at this point here and then done the product rule. We still would have come up with this. Or we could have gone ahead and FOILed this out and then finally take the derivative, and we get what we finally ended up with. Okay, number 10. Number 10, we are asked to find the second derivative, and we've got quite a mess going on. We're going to clean up this mess as much as possible before we even start taking derivatives. Y equals the quantity x minus 6, x squared plus 4x over x cubed. Now realize, once again, we could use the quotient rule, but understand when we did the quotient rule, when we did the d high, we would do ho, d high. Well, d high, we would have to do the product rule because there's a product here. Not so much fun. We could go ahead and FOIL this out and keep it there and have a quotient rule. Quotient rule, if you can avoid it, you probably want to. I mean, it's sort of nice to say ho-de high minus hi-de ho over ho-ho, but it, you know, it's a lot of work. So I might avoid that. But what I might do is, understanding that there's only one term here, what I'll do is I'll go ahead and FOIL this out. Then I'll give this x cubed to everything, and then it's just take derivative, and we'll find the second derivative pretty quickly. So that's what I'm going to do. I'm just going to FOIL this top out, and I get x cubed plus 4x squared minus 6x squared minus 24x all over x cubed. Straightening the numerator up, we get x cubed minus 2x squared minus 24x over x cubed. Then I'm going to give the x cubed to everything. So x cubed over x cubed is 1. Minus, okay, 2x squared over x cubed is actually negative 2 over x, but that can be written as negative 2 x to the negative 1. Just taking two steps at once. Minus, okay, 24x over x cubed is negative 24 over x squared, or negative 24x to the negative 2 power. Now notice I've never taken the derivative yet. I've done all my hard work at the beginning. So now I'm going to take the first derivative. First derivative of this, it's a constant, so it's 0. Taking negative 2 times negative 1 is 2. And subtracting 1 from the negative 1 gives negative 2. Negative 24 times the negative 20, the negative 2, that's a positive 48. 48x to the negative third. That's the first derivative. We need to remember we are asking for the second derivative. Second derivative is just the derivative of the derivative. 2 times negative 2 is negative 4. Negative 4x to the negative third power because I subtract 1. 48 times negative 3 would become negative, what is that, negative 144? Negative 144x to the negative fourth power. Now that is our second derivative, but it's not in an acceptable form, so just rewriting this into its acceptable form, negative 4 over x cubed minus 144 over x to the fourth. And there is the second derivative of that mess. It doesn't really have any inclination or resemblance, to me at least, to its original, which is okay. But yet that's problematic for some students. Okay. Number 11 and 12. Number 11 and 12 is actually a situation where if you knew all of the mathematical definitions of everything, maybe it would make sense. But let's look at what it's actually saying. U of 1, well, I'm not going to write all that. I'm going to write, we want to know what is d dx, which means the derivative with respect to x of v over u. And v and u are just functions. And we know their derivatives and stuff like that. And we want to know this when x is equal to 1. So really all we need are the values at 1. But look at what we have. We have v over u. This is a quotient. So we need to think of what is the quotient rule. We have no choice but to use the quotient rule, but it's actually going to turn out easier. So let's look. D dx of v over u would be ho, which is u, d high. Well, what is the derivative of v? It's v prime. Plain and simple. Minus, okay, so this was ho d high minus high, well, high is v, d ho, the derivative of the denominator would be u prime, all over ho ho, or u squared. Now, quite ironically, this is the mathematical definition of the quotient rule. So there it is. It's shorter than ho d high minus high d ho over ho ho, but those words have a, you know, they're sing-songy, they make you laugh, they make you look stupid, but that's okay. You know what? It works. So now we ask, what is u of 1? Because we have all the information we need. What's u of 1? Well, according to problem number 11, u of 1 is 2. So we're going to put 2 times, what's v prime of 1? V prime of 1 is negative 2. Minus v of 1 is 6. U prime of 1 is negative 6. And that's all over u squared. Well, u of 1 is 2, so we're going to have to take 2 squared. Now it's just arithmetic from this point forward. Negative 4 plus 36 all over 4, which equals 32 over 4, which equals 8. So the answer to number 11 is 8. What is d dx of v over u? 8. Number 12 follows the same example, but we do need to be careful with what it actually says. Number 12 is asking what is the derivative with respect to x of u over v instead of v over u. Okay, so that's going to become ho d high minus high d ho all over ho ho. Ho d high minus high d ho over ho ho. Okay, so then we can start putting in these values. V of 2, notice it's at x equals 2 this time, so v of 2 is negative 3. U prime of 2 is 4. U of 2 is 6. V prime of 2 is negative 5. All over v of 2 is negative 3, so we're going to take negative 3 and square that. So this becomes negative 12 plus 30 over 9. So this becomes 18 over 9, which equals 2. The answer to number 12 is 2. Number 13, let's see what problem we have here. Okay, we have a curve, y equals ax squared plus bx plus c. We know it passes through the point 2, 10. Now let's just stop there and figure out what we can do with that. If it passes through the point 2, 10, that means if I plug in 2 wherever I see an x, and plug in 10 wherever I see a y, that will give me some information. So let's go ahead and do that. So I get 10 equals, well, 2 squared is 4, so that becomes 4a plus 2b plus c. Well, it gave me some information, not enough to go any further, but I do know this much now. So I'm just going to leave this here. May or may not have to come back to it later. Okay, but we also know it is tangent to the line y equals 3 at, or y equals 3x, at the origin. So That tells us several things. For example, what point does this go through? This, at the origin, well, it goes 0, 0. Now, if this is tangent to this at the origin, then that means this has the point 0, 0 also. So maybe I want to put this 0, 0 back into here and see what I get. So I get 0 equals 0 plus 0 plus c. Oh, that's fairly nice. C equals 0. That worked out sort of nice. But I also know that it's tangent to this line right at this point. Well, in order for it to be tangent to this line, what does that mean? That means the slope of this line is the same slope as this graph at this point, at point 0, 0. So what is the slope here? The slope is 3. So what we need to do is we need to realize, okay, the slope of this line we can determine by using derivatives. So let's take the derivative of this. So y prime would equal 2 times a is 2a, 2ax, plus, okay, b times 1 is b, and the x disappears. Okay, now this should be the slope. Well, what is the slope of this line? It's 3. Whenever x is equal to 0. So that would mean I should be able to plug in a 0 in for x. So we get 2 times a times 0, which is 0, plus b. So that makes b equals 3. And that's just using that information. Now it says to find a, b, and c. Well, we found b and c. The only thing we have to do is find a now. That's when we have to come back to this one. This gave us a little bit of information, but not enough to work with. Now we know that c is equal to 0, so we can change that to a 0. We know b is equal to 3, so that would become a 6. So we get 10 equals 4a plus 6. And then this becomes a really simple equation to solve for a. Subtracting 6 from both sides, we get 4a equals 4. And then dividing both sides by 4, we get a equals 1. So we found a, we found b, and we found c. And chances are this is the one that's the really confusing one, so let's go back and review. We know it's tangent to this line. This has a slope of 3, remembering that y equals 3x, this is always the slope right here. So we know this is the slope. We also know that the derivative is the slope. So I found the derivative of this and got y prime equals 2ax plus b. Well, I know that the slope is 3. So I should be able to put in 3 whenever x was equal to 0. So 3 would equal 0 plus b, and that's where the b equals 3. The c equals 0 was the fact that since it's tangent to at the origin, I also knew this went through the origin, which means plugging in 0, 0, we get 0 equals 0 plus 0 plus c. And solving for c, that's equals 0. Then, once we've got all that last minute information, we can plug in the c of 0, the b of 3, and then solve for the a. That was the original part of the problem that says it goes through the point 210. Notice we have to use everything that was given, just maybe not in the order that it was given. And then the final example, example number 14. Example number 14, we are told, under standard conditions, molecules of gas collide billions of times per second. If each molecule has diameter t, the average distance between collisions is given by L equals 1 over square root of 2 pi t squared n, where n, the volume density of the gas, is a constant, and we need to find dl dt. Now here's a couple of concerns that we might have. First of all, pi is a constant. We know pi is the number 3.14159, so on and so forth. It is a number. So that's not too bad. Root 2 is a number. 1 is a number. T is a variable, but so is n. However, according to this problem, n is a constant. So that means n, in this particular problem, we're going to treat as if it were just a number. And so the only thing we're really interested in is we want the derivative of L with respect to t. So t is the variable we're dealing with. So since t, the variable we're dealing with, is in the denominator, the first thing we have to do is rewrite it in a much more user-friendly form. T squared in the denominator becomes t to the negative 2. But everything else is going to remain down here on the bottom, because these are all numbers. And it's okay to have numbers in the denominator. It's not okay to have the variable that we want, or that we're dealing with, there. So now, dl dt simply says, take this times the coefficient, so it'll be negative 2 times the 1, so it's going to be negative 2 t to the negative third, and this is just numbers, so we don't have to do any of the hidey-ho or anything like that. Numbers are just numbers. They're a coefficient. We could have written this as 1 over square root of 2 pi n times t to the negative 2, and this becomes, it's much more obvious that this is now a coefficient, and I just take negative 2 times that. But now we don't like this negative exponent, so rewriting it into its final form would be root 2 pi n. We're going to put a t cubed down here and a negative 2 up here on the top. And this is the derivative, what we were asked to do, dl dt.